through sequential blocks of memory. They do things like prefetch, and they fetch a whole cache line at a time. So, reading random bytes all through memory isn't quite as efficient as scanning memory, but it's not as bad as the difference between random I/O and sequential I/O on a disk. Other observations, yeah?
You don't have to do paging.
Yeah, so there's not like this whole database. I mean, the whole database sort of architecture we have is oriented around this notion of data being split up into these pages, where these pages are these things that are sort of chosen to be good for reading and writing from disk. Right, so you've got this in SimpleDB, this buffer pool structure that caches pages, and we talk about what page we're going to evict and what page we're going to read in. And every time we look up a tuple, we have to figure out what page it lives on and do this sort of extra level of indirection to go find that page structure and then read that tuple out of the page structure, right? So we've essentially optimized the whole in-memory representation of data in our current database system to assume that data is going to be frequently coming and going to disk, and to optimize for that case, right? And the observation here is, if the thing fits in memory, we don't need to do that, right? Like, so we could just have a big array that contains all the tuples that's in the database, right, in memory, or store them all in a big, whatever, maybe it's a binary tree, some balanced tree structure, and just at the leaf of the tree, instead of storing pointers into some heap file, we store pointers into the actual records as they reside in this array that we have in memory, which is the list of all the records, right? So we can save a lot of this kind of having to do this, bit twiddling and packing things onto pages and all this other stuff by sort of optimizing for a main memory design. Okay, so main memory. It's a lot simpler, right? So there'd be no page-oriented access. This means no buffer pool, no free page management, none of that stuff that you guys have to worry about, right? And then we can have main memory optimized indexes and access methods. So exactly as you guys said, we're not going to be so obsessed about doing sequential I/O anymore. We're not going to be so worried about having clustered indices. We can kind of come up with these indices and access methods that are optimized for kind of main memory. All right, so of course we're not, this paper that we wrote here, we weren't the first people to say you could put your database in main memory, right? This was an idea that came up a long time ago. And one thing we were curious about actually when we started doing this work was to understand, okay, like these are the sort of obvious things you get out of main memory system. Like, what would this actually get you if you built a database system that was oriented around these ideas? So the way we evaluated this question, rather than, although we did eventually build this new system called HStore, which is a ground-up main memory database system, we started this research by saying, well, what if we took an existing database system and tried to strip out the parts of it that did things like manage the buffer pool and tried to replace the B trees with some main memory optimized trees. So we tried to kind of transform a traditional disk-based database system and do some measurements of it into a sort of main memory system. So this is this graph is showing this sort of time breakdown for this database system called Shore. And basically these little boxes here, for now just focus on the left side, which is the instruction counts when processing a TPCC new order transaction. TPCC we'll talk about more in a minute, but it's a transactional benchmark. New order is you're issuing an order to purchase a new product in this database. So if you look at this this purple graph on the left, what we've broken down is the cost to do these various different operations in this database system. Okay, this thing at the very bottom is like the 6.8% of the instructions is we spend on actually doing the stuff that accesses the data, right? Like running the selection operators and the insert operators and the stuff that you think of as being the processing of the data. The rest of it is like overhead to, for example, go through the buffer pool. So we spend 35% of the instructions in this system are spent on going into this buffer pool, which is very much like what the buffer pool in SimpleDB is, a big hash map, looking up pages, within each page, looking up tuples, this sort of extra layers of indirection. And if you think about SimpleDB, you can think about how many function calls and how much code is involved just in the sort of process of saying, I want to read record ID X, you have to go through a bunch of levels of indirection. That compared to the cost to apply a selection or the cost to actually write bytes into memory turns out to be quite significant. So this buffer pool thing was about 35% of the total instructions that the system spent. So we, by sort of making this fix a best case estimate for what we could get in speed up by going to this page-oriented access thing would be a 35% speed up. If we could get rid of all of this overhead, we'd get 35% speed up, is what this result tells us. And there's a few other things here, latching, locking, logging, and B-tree keys. This B-tree keys is essentially going to a more optimized index representation. And according to this study, we could get 16% out of doing that. Okay, so these two things together will get us about 50% speed up in the database system. Okay, if we just make these two changes. So I don't know about you, but I think if you think about a commercial product, like if suppose you wanted to go build a main memory database system product, it's kind of unclear whether saying we can get a 2x performance speed up by completely rewriting the database system from scratch, it's kind of unclear whether that's going to be a winning value proposition, right? I mean, it's a little bit hard to get excited about a 2x performance speed up, right? Because there's lots of things that might get you a 2x performance speed up. I wait a couple years and I'll have twice as many processors, right? So, why, would somebody buy a completely new database system? And by the way, this is the transactional database system that's like running your most important servers and processes in the world. Why would you go to, buy a new system if you only got a 2x speed up? Okay, so these things together get you a 2x speed up. But the question we were kind of interested in this paper was, well, could we do better? In particular, there's these other three boxes here, locking, latching, and logging, that represent the other sort of about 45%, right? So this kind of suggests, this 6.8% suggests that, maybe if we could get rid of all those things, then we'd be talking about a 20x speed up, right? And a 20x speed up sounds pretty exciting. A 2x speed up doesn't sound that great, right? So there's this kind of, Amdahl's law thing or something that says that, like, the biggest, even if we get rid of 2 of these purple boxes, right, the remaining 3 purple boxes are still like way bigger than the little white box at the bottom. And so unless we can get rid of all the purple boxes, basically, or most of all of the purple boxes, we're probably not going to get a huge speed up out of going to this new kind of a system. So that's sort of what this paper is about, and what motivated us to do this work was to say, look, people have said we could go to a main memory system before, but can we do better and go to this, 20x, get this kind of 20x performance gain out of a system like this? Okay? Yep.
The B-tree keys, is that for I/O? Let's take one instructions. You still have to work with B-trees.
Yeah, this is basically, I forget the details of what we did, but we basically estimated this is how much overhead, we're still going to have indices, right? So we're still going to use indexes to find the record that we want, right? But like, for example, if you were to build a main memory optimized B-tree, you probably wouldn't choose disk-sized pages anymore, right? Like, you probably would want your B-tree pages to be optimized for main memory access, like maybe a cache line size, right? Because that's going to, get you sort of optimal memory locality, right? So having these big 4K things, well, that's sort of that's very much optimized for, what you would want to do on disk, and you likely do something very different in memory. And there's lots of main memory optimized index structures, right, that are cache aware or cache conscious and trying to do a really good job of managing the index structure in memory. So you can go read the algorithms literature, and it's full of these kinds of tree-like structures that are optimized for really essentially main memory access, and B trees are really optimized for disk-based access. So it's sort of saying, if we were to go to some optimized indexing approach, it's not to say to completely get rid of indexes entirely.
This main memory thing, is it a system, or is it have to like locate?
Okay, right. So how are we going to get? I mean, right. So we haven't told you what these purple boxes mean yet, right? But this logging component, right? Logging is what a database system traditionally does for durability, right? So it's a log is what a database system is going to use in order to ensure that you can recover in the face of a crash, right? So we're going to need to do, if we're going to get rid of logging, we're going to need to do something else, and that's an interesting question, right? So people have built lots of these main memory systems in the past, and the typical way, the traditional, I would say, the most straightforward way to build a main memory system would be to say you store the primary copy of the data in memory. You use a log to record all the changes to that database, and then you periodically take snapshots of the database, perhaps asynchronously to disk. So you have a copy of the data, a complete copy of the data on disk, like a backup. It may be a little bit stale, and then you have a log on disk also that records all the operations that had been made to the database since you last took a snapshot, right? And by combining this log with the snapshot, you can recover the database, right? You can get, so if the system crashes, you'll be able to bring the database back up. So we'll talk a little bit about that in detail on what the proposal was in this paper, which I think in retrospect turned out to be a broken proposal. So, any other questions? All right. Okay, cool. So we've got these three. So I think hopefully the goal is clear. What can we say about these three boxes? So let's start off. Let's reserve the conversation for logging for a bit. Let's start off by talking about locking and latching. Okay, so in database parlance, latching is what you guys think of as being locking. Okay, so latching is the acquisition of a short-term lock to protect some data structure. Okay, so if I have a bunch of threads that are concurrently accessing the buffer pool in order to insert pages from it or evict pages from it, and I acquire a lock on that buffer pool structure before making modifications to it, that's a latch in database parlance. Okay, this is to be differentiated from database locks, which are these transactional locks that are held for long periods of time for the duration of a transaction. And this is the conventional way that transaction isolation is implemented, if you guys remember from 6033. We're going to study this in much more detail, so don't sweat the details if you don't know it. But when a transaction runs, when it accesses an object, like reads the value of bank account A, it acquires a lock. In a locking-based system, it'll acquire a lock on, say, bank account A at the beginning of the transaction. And it won't release that transaction until the transaction is completed, until it's done all of its work. And this is how we ensure that concurrently running transactions are isolated from each other. Okay, so the difference is a latch is a short-term, an object, something that's acquired in the code in a sort of short-term way to protect some internal data structure, and a lock is something that's acquired on a database object as a part of transaction processing, and is typically held for the duration of a transaction. Okay, so these two together represent, say, 27%. So as you can sort of see from what I've been saying, these locking and latching things only matter are only used in what I'll call concurrency control. Okay, so concurrency control is you need something that when there are multiple transactions running concurrently in the system, protects those transactions from clobbering each other. And one of those things is like latches to protect concurrent access to these internal data structures, and the other are these locks that ensure that we get serializability out of our transactions. And we need both of these when we have concurrent transactions. Okay, so let's think a little bit about why we have concurrent transactions in a database system. So, all right, so why do we want to be able to run multiple things concurrently inside of a database? Yeah?
If you're waiting on something?
Yeah, okay, so because there's something that might be slow, and the primary reason really is you have something that might be taking forever. You don't want to have the whole system be locked up, backed up behind that thing that's taking a long time. Okay, and in the traditional database design that we've studied, and the way that people thought about database systems, especially when they were first being built, you had lots of these long-running operations. So. Okay, so why might we have something what kinds of things that might we be doing in a database system that would be slow, that we'd be waiting for?
Accessing disk. Okay,
great. So the first one is accessing disk, right? So obviously, if you've got good. So disk is slow, right? If we have to do a sequential scan of something file or read in 100 index pages, that's going to take seconds, right? We can have some other concurrent transaction that can just read something out of memory because it happens to be in the buffer pool and it can complete while that's happening. Well, that's good because the database system can, the disk can be doing its work and reading in pages while the database system is working on other transactions. Okay, but it sounds like if we go to a main memory system, maybe this is not an issue in a main memory system, right? Because we've got the database. Okay. But there are other things that database systems do that we might do that would be long running that would want us to still have this kind of concurrency control stuff. So what might those be?
If you didn't have column store, you needed access a single column of every single record.
Okay, so he said if you didn't have a column store and you wanted to access, a single column every record, or put differently, if you're doing a query that does like big sequential scans of the whole database, I mean, even if the whole database fits in memory, those could still take seconds, right? Like on a 1 terabyte machine, the system can scan, I don't know what, like 16 gigabytes of memory a second or something. So it's still going to take many seconds to scan the entirety of the main memory of an in-memory database. Okay, so we'll call these long-running queries. Okay. So the sort of observation here is that if you look at, and this is an observation that is sort of born out of the way the database systems have evolved over time. The way that almost any production database environment works is that there's, as we talked about, this kind of transactional system, an online transaction processing system that is loading data into this analytics system. Okay, and this is where these are short-lived queries. Okay, and these are the slow scan queries. And this is just the way that production systems generally get deployed. And the reason for this is because, well, even if you think about some company running Oracle, for example, or something, if somebody goes and runs a select star from database, right? And that select star from database requires a lock in every object before it accesses it. That's going to completely prevent this OLTP system from being able to make progress, right? And furthermore, these long-running operations are going to be consuming a ton of resources on the system that might otherwise be processing, on behalf of hundreds or thousands of clients. Okay, so just the world gets separated into these, transaction processing systems and then these analytics systems, and they really are pretty disjoint in the way the deployments happen. So maybe, if we considered building a transaction processing system that's really specialized towards this idea of short-running queries, maybe we can just say, we won't allow these. I mean, what if we just said, sorry, we're not going to run queries that do sequential scans? Okay, so that could be sort of a design principle, and if we accept that as a design principle, because this seems to be the way people are building systems anyway, maybe we can make our system go faster. In particular, maybe we can say we don't need concurrency control, which is what we're going to say. All right, so what? So there's one other case, I think, that of long-running things that these early systems, that database systems were originally conceived for, that I think doesn't really exist anymore. This is what I would call sort of interactive sessions. This is like, I don't know, you guys are probably you're probably too young to have actually ever gone into a travel agent's office or something. I don't know if this is something the travel agents even exist anymore. But it used to be that when you wanted to go make an airline reservation, you would walk into this travel agent's office and you would sit down and you'd say, I want a flight to, whatever, San Diego. And they would sit down and they would type into a terminal. And when they're typing into a terminal, they were literally making reservations in a series of database systems as they did that, right? So they would reserve the first leg of your flight, and then the second leg of your flight. And as they did those reservations, they would be holding transaction locks on objects in the database through the duration of that thing, right? Systems basically don't work like this anymore. You don't have interactive, it's not like when you go process an order on Amazon.com, there's some person typing into a terminal, right? And in fact, in fact, Amazon has gone so far as to the way they've architected their system. They don't hold. You might say, well, okay, that's a silly example. Maybe what Amazon does though is I put something into a shopping cart. You might think that that starts a transaction that updates the quantity of the number. You put a widget in a shopping cart, it updates the quantity of the widgets that are available, so that you're guaranteed that that widget that you just put in your shopping cart will in fact be deliverable to you when you hit the buy now. This is not the way Amazon.com works, right? You guys probably have experienced this, that you can put stuff in your shopping cart that it thinks it has stock for, but it doesn't actually make, hold any kind of reservation on your behalf when you do that. It goes and figures out whether there is sufficient stock at the moment you hit buy. And that can cause it to sometimes say, oops, sorry, it turns out we don't have any of those widgets left, you're gonna have to wait or something, right? And so these systems really, again, have been, transactional systems are engineered to not hold these locks for a long time. Because if you hold those locks for a long time, it prevents other things from running concurrently. So again, maybe we can just say, we're not gonna allow this kind of interactive session. So that's not to say that you're not allowed to do multiple things in one transaction, but to say that you're gonna require that all transactions be what we call one-shot. That is to say, your transaction sort of consists of a sequence of statements that are all issued together, right? So you say, like, I want to put A, B, C, and D in my shopping cart, and then I want to pay for it. And that's one sequence of things that happen, as a single transaction, as opposed to, sort of doing it interactively as things go. Okay, so if we get rid of all these things,
Question.
yeah.
So when you say that long-running queries are not allowed, do you mean it's handled in a different way, or just not allowed at all?
Well, so there's a question about how you actually would not allow it, right?
Yeah.
Like, what does that really mean to not allow it? In the systems that have been built, it's sort of like I mean, there's lots of technical mechanisms you might do, like have a timeout that says any transaction that runs for more than half a second will just be killed, right? Or any transaction that accesses more than a certain number of records will be killed. In practice, we basically just say we're going to assume that, the sort of assumption is that people are not using this system for these long-running operations, and that if you try and use the system for long-running operations, it's not going to provide the kinds of performance guarantees that we claim it provides. All right, so if we were to get rid of all these long-running operations, well, then it's kind of interesting, because we could say, well, maybe we just don't need this concurrency control stuff at all. Like, what if we just built a system that, like, a query comes in, and it knows that it's the only query running in the whole system, right? We only run one query at a time, right? So if we're only running one query at a time, then we don't need to worry about, making sure these data structures are thread safe, right? We don't need to worry about holding these long-running database locks, okay? So, right? And that then will allow us maybe to get rid of these we lost it. Will allow us to get rid of these extra overheads that you see here, this 11.9% and sorry, the 16.3% and the 14.2%. So this extra kind of 30% overhead. Okay, but I've sort of played I think I've swept something under the rug. So what's wrong with this observation? Say we're only going to run one query at a time in this main memory system. What's sort of unsatisfactory about that? I mean, we say we don't have any long-running operations. We're only doing one thing at a time, but still, maybe there's something that's it's kind of lame about this. So what's kind of lame about it?
$10,000 on a machine with 64 core.
Yeah, so these modern machines, not only do they have a ton of memory, but they have a ton of processors. And if we're only running one transaction at a time, we're only running, using one of those processors at a time. And, maybe if we think really hard, we can figure out how to get one query to use a few processors. But remember, these queries are not doing very much. They're updating a few records, reading a few records. Often there are strong data dependencies between one step of the transaction and the next. Like, you need to read the previous balance and then update it. So you can't run those two things you can't run those two things concurrently. So it's hard to get intra-query parallelism on these transactions. So the problem with this is that we end up in this sort of, again, unsatisfactory state where we can't figure out how to do multiple processes. And furthermore, furthermore, we would like to be able to use multiple machines if we can. Okay, so the observation we had in this paper, and I think it's an interesting one, although again, there are some flaws with it, and I'll talk about a few of the flaws now, and we'll come back later and revisit this kind of design. But the observation we had in this H-store system was that you could deal with this fact that you want to use multiple cores by effectively logically splitting your database into a bunch of little databases, right? So the database community likes to call it sharding, okay? So splitting your database into a bunch of little databases, right? So I'm going to call this partitioning, but if you see people talk about sharding, it means basically the same thing. So if we split this thing into a bunch of little databases and then we run one transaction per little database, then we can exploit multiple cores, right? Okay. So the question is, can we really effectively shard most databases? And if you start thinking about it, actually, it seems like a lot of the common examples that you use a transactional system for do shard pretty well. You think about the idea of a shopping cart, right? There's usually kind of like one user. There's probably shopping cart is a tough one. Take bank account balances, right? Bank account balances or email accounts or something. Almost all of the operations that happen to an email database or to a bank account are on behalf of one user, right? So we can pretty effectively partition the database by user in those settings, and then end up with one little database per user. And you can have one transaction running on behalf of every user in parallel. You've got a ton of users. You're going to get lots of parallelism out of the system. And we don't have to set any locks at all. I mean, we sort of need to have one lock at the top of each one of these partitions to make sure there's only one query running per partition. But we don't need any of this fine-grained locking or e.g. by. Okay, shopping carts are trickier. Like you think about the case of a e-commerce or retail setting. It's trickier because you have multiple users that are concurrently buying the same set of items. Right, so you can't really just partition by user because each user is going to be updating. It's going to be updating the quantity of some items that you have. Right, you can't really just partition by item because each user is going to want to purchase multiple items as part of a single transaction. It turns out in this TPCC benchmark is a retail benchmark, and in a lot of retail settings. You can kind of get away with partitioning by at a store level. So you can sort of assume that each user is only in one store or one warehouse at a time, and that will get you some parallelism. Of course, you may not have a ton of stores or warehouses or whatever that are fulfilling orders, but this will give you some degree of parallelism. Okay? Okay, so this sharding technique will get us parallelism. Of course, right, we don't want to forbid people from running transactions that access data across these shards, right? If we said you can never access data in one transaction that's in two shards, that would be bad, right? But the observation is that most of the time, most transactions will only go to one of these partitions, and hopefully that will be a win. Okay, when we have multi-partition operations, basically lock all partitions. Okay, so we're allowed to have at most one transaction running on a partition at a time. Some transaction wants to access multiple partitions, great, it just sets the lock on multiple partitions. So this will be fine as long as most of the transactions don't do this multi-partition thing, because then we'll end up with transactions waiting for each other. And this little observation does make things complicated. We'll come back to this later, but you can imagine that you can get into situations where you have deadlocks, where you have one transaction waiting on partition one, and you're waiting to get holding a lock on partition one and waiting to get access to partition two, and another transaction, holding a lock on partition two and waiting to get access to partition one, and something bad has happened in that case.
When you say all partitions, you mean the ones involved in the
all partitions needed.
Okay.
Needed by operation. Thanks. I mean, of course, you could lock all the partitions in the whole database, but that's more conservative than it would be. Okay, does this make sense? Questions? Yeah?
These partitions usually static. So you can imagine if you have multiple queries in hand, then you can dynamically partition them based on how parallel they would be.
Yeah, so this turns out to be like kind of an awesome like problem to think about because there's lots of ways you might deal with this, right? So the simplest way to deal with it would be to try and, well, the simplest thing to do would be to tell the user that they have to specify upfront a predicate that partitions the database. So the user would say, I want to partition by account ID, then you would have one partition per account ID, right? But as you say, there's lots of other interesting things you could do, like for example, take the graph of all of the objects accessed by all of the databases, all of the queries that had run recently, and somehow partition that graph up into little, independent chunks or something, right? And so, in fact, people have worked on this kind of problem, like applying dynamic partitioning to this. The problem with these kinds of dynamic partitioning approaches is that now the set of records that is in a given partition has to be maintained as like some big list. Like it can't just be defined by a single predicate. It's these big lookup tables that you have to consult when you want to figure out where a transaction is. And it makes the whole thing complicated. It's not, probably adds some overhead. But, you may not have the real luxury to take in a system like this where you're trying to do super high throughput transaction processing. Yep. What's that? Do you still need a query optimizer? Well, I mean, so query optimization matters less probably in this transactional world, right? Because what query optimization really is about is avoiding the really, really bad case where you join things in the wrong order and it causes the number of operations to be order of magnitude more than they need to be. In this, the joins are all these key foreign key joins that don't really have this kind of big blow up attached to them. They're only accessing a few records. So query optimization gives you something, but it's not clear that it matters nearly as much in this kind of setting as it does in the more kind of analytic setting, if that makes sense. So these systems still have optimizers, but they may not be, the cost models are typically pretty simplistic. They may be kind of heuristic in nature, like we'll just push down all the filters. I mean, you want to do some simple stuff like that, right? Like apply the filters first, but it might not be as complex as the full design. Okay, so what this has gotten us basically at this point, we figured out we got rid of buffer pool, we got rid of latching, we got rid of locking, we got rid of B trees, and we're left with this 11% for blocking. And I would say this is the kind of weakest part of the system, the paper, but let's talk a little bit about the design. So the proposal that we made in this paper was to say, we're just not going to do locking, okay? We're going to make the system be durable by having multiple replicas of every partition. So every partition will exist not on one machine, but on multiple machines, okay? So logging gets replaced with replication. And this is probably, the thought was, and I think this is true, in most of the database system deployments, you have replicas anyway. Like if you care about your system being highly available, which you generally do if you're in a production database environment, like Amazon, like just because their database server crashes, they can't stop processing orders because like every second they're down, they lose $1 million, $10 million or something, right? It's terrible. Like they can't have that database system go down. So they have some replicas that are there anyway, processing these, that are available to kind of take over in the event of a primary database failure, or maybe absorbing multiple database systems that are kind of together and collaborating to process all the queries that they run and can cover for each other in the event that one fails. So we'll talk much more about replication in a couple of weeks, but we could replace logging. The observation here is, well, we could just replace logging with replication. If you have standbys that are in sync with, so every transaction gets run against multiple replicas, then, maybe you just don't need logging, because if one of the systems fails, well, you just fail over the other one, and it's got all the transactions that it runs. And that system failed, and it comes back up, but maybe it can just come back up by like copying its state from one of these remote ones. So that was kind of the proposal, which is that you run all transactions on K replicas, and then you recover by copying the state. from some remote replica. So this in fact will allow you to make this logging overhead go away. What do you guys think about this as a proposal?
So won't that introduce the overhead to keep the replica?
Okay, so first we have to keep the replicas in sync. So there's a question about how you do this. If these replicas, if these partitions are exactly identical, the sort of what we claimed in this paper, which I think you should take with a grain of salt because I think it's probably not true, is that, well, you just issue the transactions to each of these, you just, the coordinator, whoever's running the transaction, make sure that the statement goes to all of the replicas. And then, as long as you believe that the network is reliable and doesn't drop messages, and that you've waited for at least a transaction, sort of a network round trip, then all the replicas will see all the messages in the loop. The challenge is that, although you might be able to have a local area network that is reliable, in the wide area where you want these replicas often to be physically disjoint from each other, like in separate data centers, to tolerate failures of the data centers that happen. This, network partitions and packet losses and arbitrary delays happen all the time, so it's hard to really make this work actually super well in practice. We'll talk in a little bit, in a couple of lectures, about this two-phase commit protocol, which you guys probably saw in 2023. Two-phase commit is a way that you can ensure that two replicas all have both received some set of messages, but it has overhead because it requires you to send a message to all the replicas and then receive an acknowledgement from all of them that they in fact have processed it. And that itself adds latency, probably latency on par with what it would have taken to write a log record out in order to commit a transaction if you're in this kind of logging scenario that we're trying to get rid of. So it's not clear that this replication thing can actually be made to work practically in a way that allows us to get around logging. Yep.
So maybe if you've only got, if you haven't replicated yet because you're small, this introduces another overhead, but if you've already replicated anyways because you want it to be highly available, maybe this overhead is already accounted for.
Right, so you're already paying for high availability overhead anyway, so maybe it's already there. I sort of agree with that. And that's certainly what we were thinking when we proposed the design in this way. So in practice, Mike Stonebreaker, as Mike Stonebreaker wanted to do, went off and started a company trying to do this called LoadDB. And the sort of feedback, at least the word of mouth feedback that I heard was that people didn't really like this design, that many people are not comfortable with the idea that the data is not persistently recorded on some disk somewhere. Even if you can convince them that in theory this could work and the system is always available, people really like the idea that there is a disk somewhere that has the data, they can make a backup of it, they can put it in a fireproof box somewhere or whatever. Right? That's important, and you can see why it's important. And so, in fact, this company that Mike started, LoadDB, has introduced a logging-based system. It works a little bit differently than a traditional logging-based system. And if we get a chance when we talk about how traditional logging works, I'll kind of walk you through some alternatives and ways that you can make logging pretty efficient. And I think you can make a logging system that's better, much better than this 10% overhead that we're seeing here in this conventional system. So, yeah. Well, typically, what we would talk about in this, typically the way people deploy these highly available systems is they just replicate the whole data. So machine one is your database machine, and you just have an exact copy of that machine, somewhere else with exactly the same data. That's the standard way people do replication, because it's the kind of easiest way to deal with the failure of a machine. If your data center goes down, or your machine goes down, you have an exact copy of your database that you can point all of your front-end processes at that they can start running against it. Right? So it adds overhead, but it's sort of if you really, really care about having, if you're Amazon and you make $1 million a second, you lose $1 million a second when your database goes down, the extra $10,000 that you pay for that extra database machine that's, sitting across the country is, completely negligible compared to the cost of an outage. So it's completely worth it to use. For, some average web developer who's got some little website, whether it's worth it to pay for a completely separate machine, it's not entirely clear, but you don't have to be very big before making sure that your data is highly available becomes super, super important as an organization, right? Well, look, a terabyte is an insane amount of storage. A terabyte is an insane amount of, it's just like, it's like you guys are totally spoiled, right? It's like, you've got I got 3 terabytes in my laptop, It's like, it's ridiculous, this is like, it's trillions of records that you can store in that much space. So yes, it's a waste, but again, these machines are not, these aren't $100 million machines. They're you know, I mean, like, it may feel wasteful in some ways. These backups and other things like that are just sitting there essentially doing nothing, and there are millions of them all around the world, right? But it is the way that these conventional systems get built, is with replicas and standbys. They're just there, basically doing nothing to deal with the 1% probability case that some are less than 1%, 0.1% of the time when the primary is offline or unavailable. So, yeah.
Can't you actually use replicas to parallelize your protocol?
Yeah, you can. So there, I mean, and again, we'll talk about replication in more detail, but the challenge with using the replicas is that if you want to do updates are tricky, right? If you want to do updates on multiple replicas, you have to sort of decide whether every update goes through one master node and then gets propagated to each of the replicas, or whether each of the replicas is sort of the master for some different piece of data. And designing this is tricky. Of course, these replicas, if they're in sync with the master, can be used for read-only queries. So if you have read-only queries, you can do that. And people do this all the time. I mean, simple, like if you're a low-end organization, for example, a common thing you might do is you just run your analytics on your replica, right? Because that thing's sitting there and it's not really doing anything. And well, you can run your long-running analytics queries on the replica because it's not doing anything else anyway, and you might as well use it. And let the production system, that's the front end thing, handle all the transactional work. Other questions? Yeah.
How does this context get done database?
So it's just like these are SQL-based systems. I mean, I think you should think of so the question was, how is this different from document-oriented databases? I mean, so there are these document-oriented systems in the world. There's this whole NoSQL movement, and we'll talk a little bit about what NoSQL means. It means different things, right? So sometimes NoSQL means it's basically a transactional data model, but with a different interface to it. So that's like MongoDB, which is probably the most common document-oriented system. It's basically a transactional database system, but where the objects that it stores are these nested hierarchical documents. There are other systems where, other cases where what NoSQL means is, it might have a different looking front-end interface, but it also throws out a lot of the other stuff, like transactional processing or other things like this. So this is, sometimes people call this new SQL, if you want a buzzword for it, but new SQL meaning it's still SQL, right? It still runs SQL queries. It's still fully transactional. We haven't given up any of the transactional guarantees the system provides, but the idea is hopefully we can get much higher performance out of it. Okay? Yeah?
One of the replicas so like if your original database went down, you go to the stuff, and then it comes up with a you need like logging on.
Yeah, so I mean, again, this I wrote this sentence here without saying too much about what I mean, but the proposal in the paper is a system crashes, its memory is gone, it comes back, it has to get that memory from somewhere, it copies it from some remote network. So in that way, it can stay in sync. Obviously, this is an expensive operation. It's going to be slow to copy all of the data over the network. In a conventional replication system, what they do is something slightly different, which is that they keep a log. They keep a log, and they usually do replication via log shipping. So when what the replica just is basically consuming the transactional log of the primary, and then when you do failover to the replica, the primary will come back, and it will be the new replica or the new backup, and the one that you failed over to will maintain the log for the duration that the primary was down. It'll ship that entire log over to the recovering node, and the recovering node will replay that log in order to get it sync. And obviously there's some fiddly little details that happen about making sure that you get all of the transactions that happen, because while you're copying this log, of course, there still are new transactions running in the system, and so there's this little switchover point or some little, you have to do something clever to kind of make this work out. Like typically the easiest thing to do would be to stop running transactions for a minute on the primary so that you're sure that the replica has all the transactions, and then you can switch the primary to the backup, or you can be ensured that they're in sync or something. Okay. All right, so what do you get by doing this? Well, the paper has a very sort of brief evaluation, but we ran this TPCC benchmark. So TPCC is the Transaction Processing Council, is this benchmarking organization. They still exist. They produce benchmarks, treat TPC A, B, C, D, E, and so on. TPC C is probably the most commonly used transactional benchmark. So this, it's relatively simple, but it models a sort of retail setting where you have customers who place orders at particular warehouses. Warehouses have stock levels of certain products. So this is the schema, but there's a customer object, an order object, a warehouse object, and then there are districts, multiple districts per warehouse. Basically, districts are like stores. Okay, so these, if you look at this, you can sort of, turns out if you look at the TPC queries, you can figure out that most queries go to exactly one warehouse. There's a small fraction of queries that go to multiple warehouses. So actually, partitioning TPC on warehouse will allow you to get pretty good parallelism out of it. It's not perfect parallelism, but most transactions become transactions that just go to one partition. So when we did this, we built this prototype system, this prototype HStore system, which is super simple. It doesn't do much of anything except for, it has one of these main memory B trees that it uses to store all the records. You've got, n of these main memory B trees, where n is the number of partitions you have, and then you issue these queries by going and doing these, read and write operations on these in-memory B trees. We don't have any logging, we don't have any locking. It's actually a pretty simple little prototype to build. When you build that prototype and you compare it to the performance of an Oracle database, in this case, what we found was this prototype, which we called HStore, was able to run, I think it was 83,000 transactions per second. Sorry, 70,000 transactions per second. Okay, 70K versus Oracle, which we hired a database administrator to tune and build the fastest implementation of it he could on the same machine we had. He could only run 850 per second. Okay, so 70K per second versus 850 per second, so like a factor of like almost 2 orders of magnitude faster, almost 100 times faster. Okay, and it's kind of not surprising because like we're not doing anything. This HStore system is super, super simple, right? It's just accessing this in-memory index structure and doing reads and writes to it. It doesn't have to do any of this other kind of overhead. But it sort of bears out that chart that we showed at the top that suggested maybe you can really get a 20x speed out of this. So this is kind of the impetus of this HStore system. And there have been, at the same time we were doing this, and there continue to be a number of these kind of main memory database systems that are coming out. And people have really innovated a lot in terms of, alternatives to this partitioning-based approach. So the partitioning-based approach, although it's kind of a clever idea, it has some limitations. Like the data you have to be able to partition the database, and not all databases are going to partition super well, right? And it's susceptible to skew, because if you have some partition that's really hot, like one of these warehouses that ends up processing a lot of the load, you can't recruit multiple processors to help, right? You can only run one processor on that warehouse, and if that warehouse is doing even 50% of the transactions, you're gonna have to basically be completely bottlenecked by the throughput of that single warehouse, and the other warehouses are just most of the time, the other processors are most of the time running idle. Okay, so partitioning isn't perfect, so people have done a lot of innovation in terms of what are alternatives to this partitioning thing that can make these main memory systems go really fast. People have looked at new ways to build these logging and replication systems to make them go fast. So what we'll do probably in the last part of this course is read just a couple of these papers about different design points around these. How do you build optimized data storage systems to deal with some of these other cases? And we'll revisit some of the design decisions made in this paper once we've kind of explored a little bit more about how transactions work. So I wanted to use this paper sort of as a way to just introduce the idea of transactions, get us to think a little bit about the kinds of systems we're trying to build when we build transaction systems and recovery systems, which we're going to do for the next few weeks in the class. All right, any questions? Okay, let's take a 5-minute break, and then we'll come back, and I want to just talk about this part 2 of the problem set. So 3:30. Yeah, that's totally fine. But we can probably have storage for you.
So there's like a lot of pointer things happening.
Okay, yeah, that's the bottom. Yeah, that's fine with me. I mean, yeah, that's absolutely fine.
Why is
At least it's good. Yeah, well, yeah, no, it's fine. I think it's good. I think it's good. I mean, I don't know what the quality is, but it's probably decent. Like enough that you can actually.
it has to be
It'd be
legal.
awesome for today. But actually, my question was about like doing the test, like what things are like. So the last piece that was supposed to be like the big test review. So is like understanding all the concepts that go into that piece that like a good.
So I think
and
the VSET is the VSET is
Sure.
the main test.
So will you attend tomorrow's
Yes, probably.
probably?
Yeah.
Will you also do
And hopefully just answer.
I try to record everything I can for classes, so hopefully it'll be recorded.
Oh, okay. So if you did, could you, would you mind sharing with me? Because I will be away.
Okay, a lot more explicit.
Tomorrow and
So-
Hamilton.
What I'm doing is, because everyone's asking this too, so instead of trying to get everyone what they want, what I'm doing is I'm just, whatever I have on my computer is slowly being put onto YouTube.
And how do I find that link?
So I will post a link on Piazza to my channel where you can find all the videos. And they'll be tagged with the classes course on them. Yeah. But I needed to ask Sam if I could do it today. So none of them are up yet, but today it's going to start. Yeah.
Just know, like, I don't want to.
Oh yeah, that's okay.
Oh, great, brilliant,
My internet is fast enough.
Yeah, okay, so again, that's conversion control is about recording multiple lines, right? So this is this partition system. And you're right, it would be go for partitioning, and where you have one transaction at a time.
The problem is I've also done
all the other clients that
Yeah, I like it.
So all the clients are going to kind of line up.
Hopefully.
In this partition case, at least we can have one client running per partition, right? So that's basically. And I mean, any database system, I mean, any high throughput system in general is going to have this, like, some requests are going to be worse than they don't want to, like, at every request of the world be processed. I mean, yeah, but servers Sure. A latch is like, it's like I said, I need to insert a page into the form. Okay, so I acquire a latch on a hash table that is, so that I can make a modification to it and be sure that there's not somebody else concurrently modifying the data. So these latches are like what you would conventionally use a lock for to prevent concurrent accesses to some internal data structure stepping making the data structure itself. Okay, a lock is because to provide transactional guarantees. We'll talk a lot more about locking, but to provide transactional guarantees, like if transaction 1 reads bank account balance A, updates, and then transfers money from bank account A to B, and transaction 2 transfers money from I don't know, B to C or something, right? Like if you don't set the locks properly on those objects, then you get into trouble because transaction 2 might read the balance of bank account B before the update happens. And so, I mean, it's a similar concept, but the idea is that these locks are more, they're almost like conceptual. Like you need to lock this record because somebody else might be accessing it concurrently. And you might have multiple locks that are outstanding at the same time, and you can withhold the locks for the duration of all the operations. Whereas a latch, like you acquire the hash table, you make one modification, All right, guys. So, I wanted to talk specifically about, I don't know how much you guys remember problem set 2. It may have completely escaped your memory at this point. So this is this problem with the patients, users and patients and relatives having, users having tests run on them, or collecting data sets and then having these tests or these results produced on them, and the users have relatives, okay? So we gave you some statistics about this table, and we asked you these kind of query planning style questions, like what would be the best way to do a select star from results or something like that, right? Okay, so I wanted to talk about the second part of this, which was to run this particular query. And this is, as you guys I'm sure remember, was kind of is a bit of a tricky query, partly because of this subquery that's here. So these kinds of questions, like a query that does foreign key joins across 3 or 4 tables, like these are the sorts of things you should be prepared to be able to answer for the exam. Like, what's the right way to order these different joins based on the cardinality of the tables and the sizes of the tables and other things like that, right? This particular example is tricky because of this subquery, all right? And the reason it's tricky is because basically what this subquery results in us having to do is to run sort of one instance of this select for every one of these UUID tuples, right? So this is what's known as a correlated subquery, and it basically means that this inner subquery here gets is actually parameterized by some value in the sort of outer query. And so literally what this means is run this query once for every UUID, run this query, find the maximum R timestamp for that UUID in the results table, okay? And so it may, you might think that you're only going to have to do 4 joins here between users, relatives, data sets, and results. But actually, to process this query, you're going to end up probably doing a 5th join, which finds the maximum timestamp for each UID, and then filters by disorder probability. And you also, the other thing to realize is that you can't push this filter on disorder probability down into this subquery, because what this is actually doing is it's saying, first find the maximum timestamp for every patient, and then for those maximum timestamp patients, filter out the records that had this disorder probability greater than 0.85. Right, so you can't filter disorder probability 0.85 and then find the maximum. You have to do it the other way around. And because of the way SQL works, there's not really a way to tell it to apply that filter after it does the maximum, except for by putting the maximum operation into a subquery in the way that we've done here. Yep.
So help understand the syntax. So if you added from results, comma, users, then it would only run 1 time, right?
From results,
in the subquery, it was from results, comma, users.
It would in this case, but that's sort of a syntactic trick, because then, if you want to think about like the scoping rules for SQL, in that case, UUID would be a reference to the inner users table as opposed to the outer users table. It might actually give you an error and tell you that in that case, UUID is ambiguous, and it doesn't know whether you mean the internal users table or the external users table, the one that's the external users table.
Would RUID be ambiguous then?
That's an interesting question. So I guess it's not. Well, we gave a special name to it here, but you're probably right that it doesn't. I mean, this query in fact will run on Postgres anyway, so it seems that Postgres does the right thing. But yeah, you're right. If we put users here, then it might mean only run this query once, and don't only run this query for this specific UUID. But it would be semantically, it would be a different query if we did that. It's not the same query. Okay, so if you think about this, you might, some of you may have done this, I don't know if you did, but there is a semantically equivalent rewrite of this query that will make it much faster. So you can actually do what's called, you can decorrelate this subquery. So you can, you can convert this subquery into a group by on UUID, I think. And in the solution I wrote it out, but you can convert it into a group by on UUID, and so you can sort of decorrelate the query, and by decorrelating the query, you can make it so that you don't have to run one instance of it per subquery. But I'm going to walk through the runtime and evaluation of the case where we do run it with where we don't decorrelate the subquery, where we run one instance of this per external UUID.
Do query optimizers do that? Correlate them sometimes?
Yes, they can sometimes do this. There's a paper I can point you out that talks about the cases in which they can do it. I don't believe they would be able to do it in this case.
Okay.
So, but query optimizers are capable in certain cases of doing this kind of decorrelation. I think that the name of the paper is like magic decorrelation or something, because it's one of these things that's like kind of surprising that you can build an optimizer that would figure out how to do it. Okay, so let's walk through the runtime of this, assuming that we're actually running this subquery once per thing, right? So, oh, I need to use 2 boards to write this out. Okay, so right, so what we're going to have to do, and the way you want to approach these kinds of problems is to think about what's the, we want to think about what's the right way to order these joins. So in this case, we have these sort of, 1, 2, basically we're going to have the 3 joins to join the 4 tables that are listed there, plus 1 more join to do this correlated subquery thing. So we have 4 joins we have to order. We want to think about what the right order to run them in is, right? And the right order is going to be constrained. Typically you're going to want to not run cross products, right? So even though you could take cross products, you probably aren't going to actually take the cross product of any 2 tables. So in this case, there actually are quite a few ordering constraints, right? Because the top part of this, those first few joins there, this the relatives joins with, we sort of have to join data sets with relatives and then relatives with users, and those 2 joins are sort of like, it probably doesn't make sense to run those until we've already have users tuples to feed into that thing. So it's probably going to make sense to run those two kind of at the end, and then to process the users joined with the results data set first, right? So the kind of question is, how do we do this users and results, and then join that with relatives and data sets? Okay, so let's just think. So we've got our users table. Let's just write out all our tables. We've got users. Well, somebody want to propose. So what do we think? What do they think we should do? What's the first thing that we should do? At the bottom of the query line. Let's
filter users.
Okay, so filtering users sounds like a pretty good thing to do. Why do you think filtering users is a good idea? First of all, users is one of the only things we have a filter on, but the filter's not that selective. It gets us 50%, right? But why is it a good thing to start? Maybe, why, intuitively, maybe does it feel like starting with users is a good thing? Okay, we have to do a subquery for each user. Okay, but, and you guys, what were you going to say? Yeah, and because the UID kind of every, we're going to sort of do this sequence of joins where every join basically ends up involving, almost every join ends up involving UID all the way up. And furthermore, it sort of feels like users is actually the smallest of these tables, right? It has the fewest records, and so you kind of, if you think about these query lines, generally you want to arrange them so that you don't want to have some really giant table that's the first, giant set of results that's at the very bottom that's being fed through all the later joins. Because if I have something that's orders of magnitude bigger than the other things, and it's it ends up being involved in every join, then that's painful. So you generally want to defer these really big joins, or joins that produce lots of outputs, to late in the query plan, so that those big results don't end up having to propagate their way through every query plan. Does that make sense? Okay, so I think starting with users it seems like a good idea, and we're going to filter it. Here, I'm going to actually write a little bit lower because I'm going to run out of workspace. So users, and we're going to do this filter one, right? And so we had 10 to the 6th users. The filter filters out 50% of them, so we have 5 times 10 to the 24, right? Okay, and we're going to want to join this with something. So what should we join it with? So what options do we have to join? Okay, so we could join it with results, right? So is joining it with results a good idea? So if we join it with results, look at the cardinalities here, right? So the results is 10 to the 8, and users is 10 to the 6, right? So that suggests that every user has 100 results, right? So when I join this filtered users table with results, I'm going to produce something that is like 100 times larger than what I had before, right? And you know, there's this filter on results which only passes 15% of the tuples, so actually it's going to be 15% of 100 or 15 times larger. It's not going to be 100 times larger, but it's still going to blow up the size of this thing a lot, right? And the other thing to realize is, so I think actually joining on results is probably not a good idea, especially given that we have this subquery that we're going to have to run that we know is going to kill us, right? We kind of get the sense, especially in the first version of this problem where we said you only have sequential scans, right? This subquery is going to be far and away the dominant cost, because for every one of these users, we're going to have to go through this subquery that scans all of the results, right? So I think the right thing to do at this point is to actually do the subquery, because we've got this users table, and every one of these later joins that we're going to do, if we were to join it with the users table, would only make the users table bigger, which would only cause us to have to do more of these indications in the subquery. So the kind of intuition is, let's get this subquery out of the way as quickly as possible, and because it's this point where we have the minimum number of users records that we sort of have to pass through. Does that make sense?
Do you need to join results to do that query, the subquery?
It's a little bit tricky. You might think that maybe you do have to join with it to do it, but what we're going to do is we're going to make the next join actually join user's ID. So sort of think about what this subquery is going to do. We're going to pick up the maximum timestamp for this given user ID, and we're going to join it onto the given user ID. So now we have user ID maximum timestamp pairs, and then at the next level of the join, all we have to do is to validate that the next thing we're going to do is to join this with the results table, and we're going to set the predicate of that results table join to verify that the timestamp is equal. So you're sort of right that it might seem like we can't do this, but I'll write out the predicate and hopefully you'll see it this time. Okay, so we're going to join this with our subquery, okay? And our subquery, we're going to do this subquery is going to do this scan of results, a filter on our UID equals UID, right? Okay, so it's a filter because this UUID is actually passed into it once per invitation. Okay, so we don't really have to do a join. It's just this UUID is like a constant from the point of view of this subquery. Okay, and then into this max. Okay, so the output of this thing is going to be UID max for that UID pairs. Okay, and we're going to do this once per invitation, right? And the cost, so this is one, the output of this is one per invitation, or at most one per invitation, okay? And we're going to do this 5 times 10 to the 5th times. And this is basically a nested loop swap. Because we have to kind of do it, well, we have to evaluate it once per thing, so we can't do some hash join or something. This just kind of doesn't make sense. So I know this is kind of tricky, but does this seem to make sense so far? Okay. So now the rest of this, except for this one little subtle issue with timestamps, is pretty straightforward. At this point, so at this point, what we're going to want to do is, so what do you think we should do for our next join? Yep.
You have those pairs, so maybe reduce the number of those pairs that you have. So you can join it with results again.
So if we join it with results again, then we can filter out, we can sort of filter out these, apply this disorder probability predicate and maybe filter out some of the disorders, right? So, right, so there's going to be, we think 5 times 10 to the 5th of these things coming up, because presumably we're going to have sort of one result per user, right? Okay. So the proposal was, and we could maybe revisit whether this is exactly the right thing, but the proposal was to join this with results, okay, where we have this disorder probability. Okay, so this is going to filter out all but 15% of the tuples, right? Only 15% of the tuples will pass this probability, this filter. So this was 10 to the 8th. This will be 1.5 times 10 to the 7th record filter. Yep.
So what is the UID on the max table?
Okay, So this is saying the records that come for each user. Okay, so we have one record per user, and for that user, we have the maximum timestamp of its result, right? So now what we can do is we can actually filter this thing on our UID equals UUID and our timestamp equals max, right? Because we have this max, and we have for each one of these records that's coming out, we have this timestamp, right? So, you know, if this, like, this is a little bit tricky, and the sort of, it might have been more intuitive perhaps to have done the subquery later, right? To like have maybe flip this around so that this subquery gets applied, so that first you do this join, and then you do the subquery for each one of them, but you're going to do more work if you do it that way.
So what is it that we have to break the algorithm from UND again? Does that automatically happen first?
No, it doesn't, because, right, we have a whole, like, I mean, it would only, that would only work if this timestamp were unique across all user IDs, right? I mean, we're sort of making, in fact, an assumption that this timestamp, well, we are making an assumption, I guess, that this timestamp is unique, but if we didn't, if we only applied this timestamp equals max filter, if we didn't apply this filter here, we would be in trouble, because there might be lots of occurrences of this particular max, this max timestamp that could occur across other users. Make sense? Okay, so at this point, here I'm going to start writing on this board. Okay, so like this. Okay, so at this point, right, we this max thing, it has, because we're doing this max thing, we can basically we'll end up getting 15% of this 5 times 10 to the 5th records that come out of this, right? Because only 15% of these records are going to pass both of these predicates. So we actually, this is a big data reducing step. So at this point, you have 15 for 0.15 times 5 times 10 to the 5th, okay? Records that come out. And then, you know, the next two joins are really pretty straightforward. We're just going to do these joins with relatives and data sets. And then we'll project out. And you kind of have to do them in this order because of the, if you look at the way the predicates are arranged. We sort of, for the user, we have to go pick up its relatives, and then we look at the other side of the relatives relationship and use that to pick up the data set. So we have to join the relatives before we can join the data sets. Yeah?
So what kind of join have we decided with the data?
Okay, so we asked what join algorithm should we use?
Yeah.
Okay, so in this case, we didn't give you very much information. So we didn't tell you how much memory your system had, so you kind of had to make an assumption. Probably, you know, in the absence of other information, you know, basically the right thing to do is probably going to be to use some kind of hash join, right? We don't have any, we can't really exploit any sorters here. And because we didn't tell you how much memory to use, you had, you know, maybe you could think this would fit into memory, but these other data sets are big. You're probably going to end up doing one of these external hash joins that we studied. So in the analysis that I did of this anyway, I just assumed we'd be using Grace hash. Because, you know, Grace hash is pretty good. It's 3 times the, you know, you're just going to read each data set in, you know, it's 3 times the size of the 2 input data sets. It doesn't have sorting overhead. So it's generally speaking a good choice when you're doing big joins and you don't know much about how much memory you have, and we think that we might not have. So one more question?
Is that internal practice, like determine the order in which you're going to join things and then determine the type of
okay, and so it's complicated. I mean, it's not. This is not going to be a perfect algorithm for doing it. That's generally how I would approach them. But the other thing you need to think about are these. Sometimes these sort orders can be exploited to make certain of the joins go faster. But even if you have a sort order, right? Generally, the joint ordering is going to want to be ordered from the sort of smallest table up to the biggest table. Because again, having big tables at early on is going to be bad. If, you know, I had something here where I had 1 million results. You know, I had 10 to the 8th results here instead of 10 to the 3rd results here. These two joins would be much more expensive. So I want to try and filter down the data and get keep the relations as small as possible going up. And the choice of join algorithm is a little bit independent of how much filtering down of the data I can do. It doesn't matter which algorithm I use to do joining, right? These sort order things can make it a little bit tricky. So that's the only thing on that. We'll post the solutions to this, but hopefully this gives you a sense of how to think about the ordering. And once you've done this, I think doing the cost analysis is just a matter of arithmetic. For the second part of this problem where you had indices, there are some cute things you can do with ordering. So look at the solutions because you can kind of exploit ordering to make it more.